Well, good evening. I'm Charles Schultz, and this is the Randomizer for Tuesday, February 22nd, 2022. And this is our randomizer at 6 p.m. weekdays. This is a special one today. We have a new term that's been randomly selected out of hundreds and hundreds of terms, and the term is particle. And we're going to talk about what particles actually are, what people think they are, what they really are. And we're going to disavow some misbeliefs. It's going to be a lot of fun. So everybody thinks they know what particles are. You hear all about them, nuclear physics, there's particles doing this or that. We're going to show you it's really not what you think it is. So first of all, I encourage everybody to go to universesciencecenter.com or schultzlaboratories.com and sign up as a member and get some support for some of the galleries we're building and the exhibits we're adding. Get your Oculus or your other 3D headset, walk around in there, experience it, share it with some friends. It's a lot of fun. If you're a homeschooler, you'll really appreciate it. And if you have suggestions as to what we should add to our galleries or be teaching, contact us. Send us a note. There are places to do that. And one place that you can do that is actually right here on the randomizer. Join us 6 p.m. every weekday, and that's Eastern Standard Time, for a random technical term or word being discussed. And we have like 15 minutes of that and 15 minutes open floor for questions, answers, suggestions, or whatever. So we're happy that you're here. We thank all the people who have supported us and our members. And we're just going to keep growing and try to reach everybody. This should be one of the best educational institutions on the planet, and certainly in the virtual world. So back to the subject at hand, particles. So everybody thinks they know something about particles. You've heard of electrons, you've heard of protons, you've heard of photons, and various types of radiation. And so what is a particle? A lot of people think of it as a little tiny, hard little marble or some sort of little point or something. And that's actually kind of correct and kind of not. You see, whether it's a particle or whether it's a wave really depends on the circumstance. It's a foggy world down in the quantum realm, and I'll explain. Let's say you had a big thermometer and you wanted to measure the temperature of some water, and the water is fairly hot, and your thermometer is at room temperature. Now, you drop the thermometer in, you measure the temperature of the water, and you write it down. You got a reading. Here's the problem. The thermometer was cooler than the hot water. So when you put the thermometer in, the temperature of the water went down a little bit. Taking the measurement affected what you were measuring. And if you use a smaller thermometer, obviously the difference in temperature is going to be less critical because it has less heat to change the temperature of the water to. So the smaller the thermometer, the more accurately you're going to read the temperature of the water. Now let's turn this around. Let's say we had a smaller and smaller sample of water that we were measuring with our tiny thermometer. At some point, we're going to find something very, very interesting about the temperature of the water. When you put the thermometer in, you're reading temperature, but what is temperature? Temperature is the random movement of the molecules in the water, and they're moving all around in every direction. Think of them as superballs bouncing off of each other in a big vibrating container, and that the vibration of the movement is the heat. And the hotter it is, the faster the particles are moving and the more energetically they're bouncing. And if you move it fast enough, some of them will bounce out of the container. That's evaporation. Now, if you take your little thermometer and you measure the temperature, you're getting the average energy of all the molecules striking it. Now, this is very important. If you've ever used a microscope in school as a kid, and you've noticed little particles in the water are dancing around at random, and you're told, oh, that's Brownian motion. This is where sometimes more molecules hit it on one side than the other, and it makes it jog around. So the particles are dancing about at random, and the hotter the water is, the faster they jig, and the more they move around. So wait a minute. What you're saying is temperatures of different particles are striking it giving different momentum to that particle. If your thermometer was sensitive enough and fast enough, you would see that in some samples of water, you're getting all sorts of different readings, and you'd have to average them to figure out what the actual temperature is. Some would be very hot, some would be very cold, but in the end, you would get the average. Well, here's a funny thing. I can have 2 cups of water. One has been held at a constant temperature for an hour, and one I heated the temperature, mixed it a little bit, and it's about right. Okay. And I measure the two, and on average, they give the same temperature. But with a tiny, tiny thermometer, the one that's been settled for an hour will give a very uniform temperature. All the molecules in it are moving at an average speed. They've kind of shared the energy until it's smoothed out. It's settled into some standard temperature. Whereas the one you just mixed up out of hot and cold water to get the temperature right has a wild spectrum of energies all over the map. And so if you were to measure the two and compare the samples, one would have a very smooth graph that you would average out. That's the one that has settled. And the other, and has reached what's called equilibrium. The other one would have a wild number of high and low temperatures that you'd have to average out. You may read the same temperature, but it isn't normalized. So this is what's very important. When you start talking about a particle, the same sorts of environments exist. The smaller an object is, the more wild its temperature or energy can be. Now, let us imagine a little experiment. I'm going to set a box, a cigar box, on the table. Many people don't know what that is anymore. Anyway, a small box with a lid that'll close. And I'm going to take a handful of marbles and I'm going to pour them in that box and I'm going to close the lid. Now, the box is solid, and when I pick it up, all the marbles will be in the box. If we were to shrink that down like 1 trillion times to the atomic scale and put electrons in this little box, and I pick it up off the table, half of the electrons are still on the table and half are in the box. But there's no holes in the box. How does that work? It's not a leaky box. It's because of something known as uncertainty. So people often think of a particle as being like a marble, a little hard ball. And it has a definite size and shape and amount of energy, and you throw the particle at something and it strikes it and it recoils. That's not exactly true. You see, it's not a bunch of marbles on a flat table. It's more like they're taffy or rubber or foam, and their position smears out. And the tinier a particle is, the more smeared out the probability of its position being what you think it is becomes. And this was one of the things that really puzzled Einstein many, many years ago. He even came up with a statement. Now, he felt like Descartes, that the universe was like a machine and everything was deterministic and you could plot all the little variables and know exactly what was going to happen next. And he was so outraged by quantum mechanics that he said, God does not play dice with the universe. And that was what Einstein's statement was. Stephen Hawking replied, God not only plays dice, he throws them in the corner where you can't see them. And actually, Werner Heisenberg was the first person to say something along those lines. But Stephen Hawking was quoted as having said it as well. Now, who was Heisenberg? He's the man who understood the uncertainty principle and put it forth and defined it as a set of equations. So what is uncertainty? What does it have to do with particles? We often hear that a photon, the tiniest unit of light, is a particle sometimes and a wave sometimes. That's not actually true. It is an entity that has the potential to act in either way. And it depends on how it's going to interact. If you put a prism out there to split the beam of light up into different colors, the photon's going to follow a pretty definite path. If you make a slit, a very narrow slit, and shine some light through it, it will spread out. And if you put 2 slits side by side and shoot one color of light through, what will happen is, just like waves moving on the surface of water, the light will move like waves and it will collide and make light and dark stripes, as if the particles knew exactly where they had to go. They're acting like waves when they're interacting. What's even stranger is that one particle, one photon, can go through both holes and interact with itself and make a wave. That sounds crazy, but here's why. Particles are not solid objects. They're actually grainy. The whole universe is grainy. If you played the old Mario games where they had very low resolution for the graphics, you saw the little blocky figures moving along. That's a very low resolution picture of the world. Today, video games have high resolution and look photographically real in many cases. There's more pixels, more resolution. As it happens, some experiments were done that revealed the universe is not smooth like glass or smooth like peanut butter. It actually is chaotic and granular, just like the pixels in the old video games. And in fact, those pixels are so tiny that if you had 1 cubic meter of space, the little pixels that space is made up of, the vacuum itself, would have so many, it would be like 1 followed by 105 zeros. That's how many little pixels would be in that box. An incredible number of little dots. So now think about it. Electrons, some of the smallest particles, and they're unitary particles, they're fundamental, they don't simply decay into something else, they're very stable. An electron is humongous compared to the grains of space-time. So when you start looking at an electron, what you are really seeing is something entirely different from what you expect. Electrons, even though they are matter, can actually spread out like waves. And the probability of the electron being in a certain place is shaped like a bell curve. And so at the height of the bell, you have a very good possibility the electron is there, but it might also be out here, less and less probability of that as you go farther away. But the electron has a wave. Now, this is the most interesting thing about the wave of an electron. If you picture an atom, most people think of it as like a little sun in a little solar system and little atom planets called electrons going around it in orbits like little planets, and that's absolutely wrong. In fact, if that were the case, the positive charge in the nucleus would cause the negative charge of the electron to spiral in and crash into the nucleus, and that would be the end of the matter. It's not what happens. The electron in this tiny, tiny state is more like a wave than a particle. And it spreads out into a self-interfering wave, and it doesn't orbit like a planet, but it makes a shell similar to the layers of an onion. So that the electrons around a hydrogen atom are smeared out into layers just like the layers of an onion. And when you get more than one atom together, the layers deform into strange and fantastic shapes determined by the minimum amount of energy. If you have wax paper and you put 2 droplets of water on it and you push them together with a toothpick, at some point the droplets get near each other and they merge into one larger droplet. But in the middle of the state, you'll find 2 droplets with a bridge between them pulling themselves together to merge. The electron shells in atoms are very much like those 2 stretched out droplets starting to merge. Why don't they fall together? Why doesn't the electron spiral in? It's because the lowest energy for that particle is to remain in that shell. If you were to force it to go in, that's where the electron interferes with itself destructively and can't be there. Where the shell and the electron exist in the center of that shell, that's where the waves interfere constructively, and it can exist. So you can imagine if a wave were moving in the water and another wave were to cross it, funny things will happen. Where the 2 waves are highest, it builds up to a higher crest. Where they're lowest, it builds up to a deep dimple. Where one is high and one is low, they literally cancel out. So electrons, particles in the nucleus, matter all around you actually has wave-like properties that interfere and create places where it can be and most likely cannot be. So what we think of as little marbles orbiting each other is absolutely false. In the real world, they act more like waves under those conditions. But here's a caveat. the more complicated a structure becomes, at some point, the laws of quantum mechanics merge together and make the laws of the world that we exist in. So it's kind of a voting process. If most of the particles are over here and a few are over there, the majority tends to win. And this is why something like these glasses or this pen can't interfere with each other, because the majority of the particles agree where they are, and the electron shells on the outside repel the other electron shells. You see, there is no such thing as solid matter. It's all an illusion caused by the repelling forces of the negative charges of those electrons. If something's moving really fast or something's really tiny, it actually can penetrate the matter. And some sorts of energy, like photons, often do. So what is a particle? A particle is a consensus vote, and the energy is most concentrated where the consensus rules. And that's where the majority of the votes are true, and that's where your particle is. But if you look at an electron with a camera that can see it without interfering with it, you would see the electron ping-ponging around in space, just like the Brownian motion of the particle in the water on the microscope slide. So, in reality, the quantum mechanical realm has peaks and troughs of energy, and those things make the particle jiggle around, in a sense, so that it smears out into a wave-like form. So, particle is our word for the day, and as you see, at the nuclear level, at the particle level, at the space-time level, it's really not a particle. It's a collection of aggregate decisions in the void. Quantum mechanics rules, we are simply the next set of rules that emerges from that, the macro rules. So at this point, if anybody has any questions about particles, the floor is open, and I'm going to urge you to go to schultzlaboratories.com or universesciencecenter.com. Notice the and or, that's your quantum choice. Sign up as a member, join our classes, do something to support the growth of this, share it with your friends. Let's make this thing go worldwide. This is the best educational concept there can be. It's a virtual world where you can walk around in there, explore things, and do things without any real physical consequence. You'll be able to smash planets together and put moons in orbit, and we're putting directory pages in that will show you all the basic glossary of terms, and it's going to be amazing. You'll have mathematics and physics, and there are many things in there already. Space exhibits and physics exhibits. If you go in the physics room, go to the left, and you'll discover models of the atom that you can explore and see what's in the nucleus and the table of elements. So go in, explore, and have some fun. And at that, I don't see any questions on the scope here, and I'm going to say, I guess this is a win. I'm going to read one quote before I go, and it is, "Flesh gives birth to flesh, but the Spirit gives birth to spirit." And that's John 3:6. Think about that. No matter what you do as an animal, the result is still as an animal. Whatever you're doing in your mind or your heart, that's an entirely different matter. Make the world a better place, and thank you for joining us tonight. I'm Charles Schultz with Schultz Laboratories and Universe Science Center, and I hope you have a wonderful evening. Good night.